Alex, thank you.
Thanks, Nicholas. So at this presentation, we're not going to focus that much on the application. We're going to more broadly focusing on the tools. So I'm going to talk about especially surrogate models. So surrogate models or meta models, for those of you that are not aware, are simply data-driven approximation of the input-output relationship of a complex numerical model. A little bit more on that later. In this presentation, we're going to focus explicitly on the iterative adaptive development of meta models to support specific uncertainty modification UQ tasks. So our goal here, what I mean by iterative adaptive, will not be to establish a globally accurate characterization of the input-output relationship, but simply to do good enough to be able to accurately perform the UQ task. And throughout the presentation, I'm going to try to convey the main, fundamental theoretical developments in the context of two specific applications. And for most of the time, I'm going to focus on the first one, on the design under uncertainty. So this is at the outline of the talk. Let's try and convince you why surrogate models are cool, especially overlooking on the design under uncertainty problem. So this is the system that I'm trying to design, and I have some model for it. It can be a car driving on a rough road. It can be a wind turbine exposed to wind and waves, or it can be a building under earthquakes. I really don't care what it is, but I can build a model for it. I'm going to denote as X my design variables, the controllable things related to my system that I'm trying to design, and by theta, the model characteristics, the model parameters that are considered uncertain. And since they're uncertain, I'm going to assign a probability distribution from them. So with my model, I can evaluate what the response of the system is, and then I have some performance evaluation function that pretty much gives me my performance measure A, which is, ultimately it's a function of the response, or also you can write it as a function of X and theta. Note that I'm making here a really formal distinction between response and performance. So the underlying assumption is that I have, and also my assumption is that this performance evaluation model is very simple to evaluate. So for example, if you're talking about a wind turbine, this is going to be a finite element model that comes and gives you the stresses of the different components, and your performance evaluation model is generally, let's say you're looking at the system reliability, is just going to be the indicator function over all your responses. So this part, computationally really expensive to evaluate. This part, analytic expression, very simple. Also, to complicate a little bit our life, we're going to assume that this is a black box. So let's say it's a computationally, expensive numerical simulation that you can evaluate the response, but you cannot do a lot of other things with. For example, you cannot come and get the gradients. Ultimately, this setting gives you what we call design problem under uncertainty, or uncertainty process design. You try to select your controllable parameters, your design variables that are going to minimize your expected performance, the expected value of H over the whole uncertainty distribution that you have. So this can be, for example, minimize something, design something to minimize the failure probability. So this is a single objective, and in this specific seminar, I'm going to look more at the multi-objective design. So you have multiple objectives. I'm going to use the subscript I to differentiate between the different objectives that I have. It's associated with a different performance measure related to my system response. And again, if your objectives are competing, there is no single solution, but you can go and identify the Pareto front in the objective, the space of optimum designs. And ultimately, what does that Pareto front correspond? It corresponds to the dominant design. So this is sort of your feasible objective space of your performance. Is pretty much the designs that you cannot improve one objective without a detriment to the other. So the solution to this multi-objective problem is going to be in this red curve, the Pareto front. So ultimately, what we're trying to figure out, we set up the problem. How can you really come and identify this Pareto front? Like block space representation of our problem that I'm going to use throughout this presentation. In order to solve it, the first thing that we need to do is evaluate this multi-dimensional integral. It has as high dimensions as as many as uncertain parameters that you have. And since we said we're going to rely a lot on a black box model, there's only one generalizable approach that's going to allow you to calculate this integral, and that's a stochastic simulation. This is a simple Monte Carlo simulation with important sampling. So you can come, you can substitute your objective with this objective that comes from stochastic simulation, and then you can solve this problem. This is what we call simulation-based. It falls in the greater category of simulation-based optimization, where the simulation parts come from the fact that, yeah, you have to rely on stochastic simulation. Very powerful approach, pretty much up to now. I didn't come and put any constraints on what numerical model you can use. It can be a black box here, or any probability models that you can use. This can accommodate everything. Of course, the problems are when you try to computationally efficiently solve the problem. So you have estimation error that comes from stochastic simulation that need to be addressed. The computational cost for a single objective function is really high because you need to call n times your expensive numerical model to evaluate your objective function only once, and this can be high, 500 or 1,000, depending on what the application and how good your important sampling densities are. And also, since we said, okay, we're going to use a lot black boxes, numerical differentiation in many applications is the only possibility for getting derivative information. Of course, there are some remedies for these challenges. For example, you can come and rely on important sampling, or you can come and use the concept of common random numbers to reduce the relative importance or the absolute importance of the simulation error. This is what we call embarrassingly easy to parallelize problems. So you can throw, because pretty much your evaluations within a stochastic simulation are independent. That's why we call it embarrassingly easy. So you can come and use high performance computing to simplify a little bit your life. Or you can see numerical differentiation, you cannot rely on it. You can come and use algorithms gradient free or maybe appropriate for costly global optimization. Okay, these are good tools and they're really powerful tools. In this presentation, I'm going to talk a different route, and this is going to be surrogate models. So, as we already discussed, surrogate models are data-driven mathematical, approximations from the input-output relationship. So, Y is going to be my input, Z is going to be my output of a complex numerical model, typically referenced as process numerical. So, how to develop these data-driven models? Where you go, you evaluate, you get your database, so through your computational expensive simulator, you go and evaluate your response at a number of points. Typically, they're called the training or support points, or also experiments. So these are sort of your computer experiments, and using that information, then you can create your approximation. It can be for some simpler, like a simple interpolation to a regression model, to something more complicated, something like a neural networks, response surfaces, or what, specifically for UK applications, what has gained a lot of traction, and what is really powerful is a Gaussian process meta model. So what these Gaussian process meta models do, I'm going to use the term GPM a lot from now on. Pretty much they approximate the real function as a realization of a stochastic process. So in other words, you do not specify a single model, but you're specifying a family of models, that have some median and some variance. So you can go through the mathematical applications. You can calculate what the median is. Okay, maybe the details are not important. What I would like to focus here, but here your predictions, you can see, are straightforward matrix manipulations. So, and this is a very powerful characteristics of this type of meta models, because you can easily vectorize them. So as soon as you have the meta model coming, can be able to come and do 1,000 or 10,000 or 100,000 predictions, it will take around 0.1 to 0.2 seconds. So after you get, of course, the initial database, which does require some effort, and after training the meta model, which also requires some effort, using the meta model to make a predictions pretty much requires no significant computational burden. There are some certain applications who have really large databases where there are some challenges, but for the most cases where your database is not big enough, this is very easy to vectorize and perform it very well. And on top of that, we also have a measure of the variability of our predictions, what you can, many people call predictive variance. And in general, you can, there are two different ways to think of these meta models. One is to come and consider, this is just a family of predictive models. This is more the Bayesian approach to think what these meta models, what JPMs are. The other approach is more from deterministic people, is to come and see, yeah, I do have some mean predictions, and if I want, I can just rely on the mean predictions. And then I have, sort of this gives you an estimate of the variability of your prediction error along this prediction. Both these, approaches are pretty much end up being really equivalent depending on what really your background is. So I'm going to play between them during the presentation, but you're going to see I'm going to be calling this a lot many times as, yeah, gives you information about your prediction error around the mean predictions. So really quick illustration, very simple one-dimensional problem for those of you that haven't seen meta models before. Sort of this is your exact function. You go and evaluate your exact function at your experiment, your training points. So this is the information that you have. Then you can go and train your meta model. For GPMs, this is generally the optimization of the hyperparameters of the correlation function of the underlying Gaussian process. And as soon as you have that, you can get then the predictive mean, but also you can estimate the predictive variance. This pretty much comes and tells you, what is the size of the error along these predictions. So ultimately, this is what we call that you have a family of meta models. So you not only can rely on the predictive mean, but you can play with, say this is the mean plus one standard deviation plot. So if you want to create realizations of what your predictions are, you can if you want, you can completely ignore the error and just use the blue line, or you can come and create realization based on the stochastic process. So all of these are different meta models that belong in this predictive family. And of course, the accuracy of this meta model really depends on how you select your training point. Yes, the optimization of the hyperparameters is important, but what's more critical is how you choose your experiments. You can see here, what happens if I start with 5 experiments and I put 3 more, how much better or accurate our prediction comes. Another thing that I should point out that you can see here at the predictive variance is exactly 0 at the locations where you have an experiment. And this is because JPMs, at least in the fundamental formulation, they're an exact interpolation. And then the question that we can ask ourselves, okay, is there a way to select smartly this experiment? So if I initially had, this meta model, and I was asking myself, okay, I know maybe my accuracy is not big enough, I see big variances, and I want to add 3 more points, where should I add them? So let's talk a little bit about adaptive design of experiments. So this is the information that you have. You don't know the green function, because you don't know the response. You know what the blue is, but also you have this, estimate about local estimate about how big your error is. So in other words, if you're asking, you put some more experiments, you shouldn't put them around here where you know already you have good accuracy. So you should put them, in regions when you have, a big big estimated variance of your error. And maybe you don't really care about what is the error of your response, but you can come and propagate and then sort of calculate what is this is like a Taylor series expansion, how the variability, how the error in the response propagates to the error in your performance measure, what you care about age. So we're going to call this utility metric. Pretty much it comes and tells you what is the potential utility of adding this experiment. And generally, we want to put experiments around the domains where we know that we're not doing a good job to start with. Now, another complication is that at the end of the road, you try to perform a specific U2 task. So, in other words, maybe you don't care about all the domains here, but there are some specific domains that have higher importance. So this is because there is a preference function, a preference density. If you're just looking at forward uncertainty propagation, this is sort of going to be your integrand. But in general, we're going to quantify this as a more general preference function. So in areas where the preference function has low values, really improving the accuracy, then adding more experiments, it really is not going to help you a lot. You primarily care in the domains that you have, higher values of this, preference function. Again, I'm going to come and do a couple of examples later of how we select these preference functions. So In general, this adaptive design of experiments is a very tough problem, and you can simplify it. In other words, you can do a suboptimal selection of experiments through what we call sample-based design of experiments. So how is this performed? So you start by simulating a really large number of samples based on your preference function. Then you come based on your utility metric, and you keep only the samples that correspond to a higher value of the utility metric. In other words, that have that are in regions when you don't need where you think that you have a high prediction error to start with. And then these are your candidate experiments. And of course, if you come and adding experiments that are close to one another, one's going to help the other. So you really don't need all these experiments. So what you do after you get them, you cluster them into the desired number of experiments. In this application, we wanted to get 3 more experiments. So these are my 3 experiments. So these are maybe suboptimal DOE, and you can see as soon as I come and add them, I'm able to really improve the predictions and really bring down the error. This was my previous estimated error. This is the new estimated error. So this sample-based design of experiment, it really satisfies all our goals. It gives you new experiments in domains where they're important for your UQ task, in domains where you didn't think you were doing a good enough job in making predictions, and also experiments that are not close to one another so that they don't end up helping each other. So in the remaining of the presentation, we'll never talk about a design of experiments. I'm going to come and use this simplified sample-based DOE. So in summary, going back into our surrogate models, we're going to use Gaussian processes, which is exceptionally important, especially in user applications, because they're computationally very efficient. And with manipulators that are very easy to vectorize, they're exact interpolation, and they have proven accurate even for complex functions. Also, if you want gradients, especially if you look about design, you can very easily get the gradient. So we didn't have gradients before for our black box numerical simulator. As soon as you emulate that with a surrogate model, you can very easily, again, come and get the gradients of your response. And more importantly, it gives you the predictive variance that tells you how good job that you're doing. That is a local, so it is also a function of your input. It's not constant along your whole domain, as a general regression would give you. And especially this, as we saw, it can be very important for coming and helping you adaptively select when the next experiment should be. So let's bring now these models back into our design under uncertainty problem. So we're going to come here and we're going to try and replace some parts of this whole problem with a surrogate model. And of course, the question is, okay, what space should we formulate the meta model, and what is really adaptive? For example, you can forget this pattern. You can come and say, no, we're going to create the meta model to approximate my objective function with respect to my design variable set. So this is sort of what a costly global optimization algorithms do. Here we're going to try something very different, and we're going to create the meta model in what we call augmented input space. That's composed of both my design variable and my model parameters, both x and theta. So a meta model to simultaneously look at what happens with the uncertainty and what happens with my design optimization. And also in terms of input, what I'm going to focus the meta model is on the computationally expensive numerical model. So in other words, I'm going to approximate my response and not my performance. As soon as you have the response, then you can evaluate the performance and get this modified performance measure. And I'm calling this modified performance measure because you can come and address explicitly the uncertainty in your meta model to evaluate. So this is not just coming and getting your performance function and just coming and replace the median predictions. No, you come and explicitly propagate the uncertainty that comes from the meta model. A more tangible example a little bit later, but you can see this is your modified performance measure is a function of all the characteristics of your meta model, both the mean and the variance. So how does this work? Well, you get some training points considering variation in both x and theta in the augmented input space. You develop the meta model that, again, covers variation in both x and theta. And then you use that, the modified performance measure to come and change your objective function. In that case, you can also, if you want, you can come and very easily get gradient information. Still high-dimensional integral, so we're going to still rely on stochastic simulation to evaluate it. So these are stochastic simulation-based approximations. But the trick here is that this now requires no computational burden. So you can evaluate your objective function with 1,000 or 2,000 samples pretty much on no time. Of course, the expensive part is coming and developing this meta model. But now the trick is whenever, and then now you come and replace your initial optimization with this meta model aided optimization problem. And the trick here is, because you're developing in the augmented input space, whenever your optimizer tries to search a different design solution, you don't need to repeat the whole process. You come and use the already meta model in the augmented input space. So when you go, okay, I evaluate at k, now I need to have a different iteration. So I need to evaluate k plus 1. You come and use exactly the same meta model. So this formulation in the augmented input space, it allows you to simultaneously use a single meta model to simultaneously do both the uncertainty propagation, come and evaluate these integrals, and the design optimization, come and identify what your optimum design is. So then, okay, what tool can we use to do this multi-objective optimization? In other words, what tool, what numerical tool can we use to identify the Pareto front? This is the Pareto front in a very simple two-dimensional example objective space, and this is in the design space, the sort of contours of your two objectives. A lot of people would come and do something like genetic algorithms, like a heuristic optimizer, which is a good solution, but we prefer for something that you can explicitly control how evenly the Pareto front is populated. And since we also have gradient information, my preference, strong preference is use epsilon constraint approach. So how does epsilon constraint approach? Initially, you consider the single objective optimization of each of your objective functions. So you optimize, and you get the two anchor points of the Pareto front, and then both these were single objective problems, so easy to solve. And then to solve the multi-objective problems, you consider some objectives to be constraints, and then you're optimizing for the remaining ones. Sort of you are constraining this two-dimensional problem within this domain, and then you optimize and you evaluate this point. Again, this is not a multi-objective optimization anymore. It's a constrained single-objective optimization, especially since we have gradients and a meta model, we can very efficiently perform it, and repeating that, you get the whole Pareto front. Okay, so this is the setting. Now let's dig a little bit more deep and talk about the iterative application. So the naive approach would be, okay, let's create a meta model to start with, and let's perform this and perform the optimization. So you get your training points, you evaluate your model, you develop your meta model, and then you get your Pareto front that is relying on your meta model. Now the trick here is, okay, how accurate this Pareto front is, especially since you rely on a meta model. You can come and if you had, unfortunately you don't, but if you had the actual Pareto front, you can come and compare. And generally, the more accurate the meta model is going to be, the better accuracy you're going to get in getting the actual Pareto front. So you might be tempted to come and say, no, we're going to get a globally accurate meta model, something, let's say, that has 97 coefficient of determination, 97% coefficient of determination, correlation coefficient. Since we know that it's very accurate, we're going to use that and perform the optimization, and then pretty much we'll guarantee that these gaps are going to be close to one another. But is this a really computationally efficient approach? And the question that we pose to ourselves is, okay, can we efficiently converge to correct solutions with potential inaccurate meta models? In other words, do I need to have a globally accurate meta model, or is a locally accurate meta model sufficient enough? And what does that locally accurate mean? And this is where the iterative approach comes, that we rather, let's say that we had a budget of 5,000 experiments that we thought that we could afford. Rather than starting with 5,000 experiments, start with 500 and then add 500 more. So iteratively do it so that one iteration comes and gives you better information on how to move on, how to better select your training points. So this is what we're going to do. So we're going to do it iteratively. So we already have done this. Now we're going to come evaluate some stopping criteria, like in any iterative approach. We need to have stopping criteria. If they're satisfied, yeah, we're going to stop and we're going to say, okay, this is our Pareto front. If they're not satisfied, we're going to go and improve the meta model. So we're going to come and get new training points. We're going to see how we're going to select them. We're going to come and again evaluate and enhance the database. We're going to update the meta model, and then we're going to get a new predictive front. So very simple idea. Of course, the two things that I need to answer is, okay, what are stopping criteria? And also, how exactly are we going to select, how we're going to perform our DOA to select the new training point? So let's focus a little bit on the stopping criteria. And generally, as already alluded, we're going to do iteration-wise improvement. We're going to come and compare the old Pareto front with the new, the new Pareto front with the old Pareto front and see if they're close enough. So if there's significant discrepancy, evidently we haven't converged and we should continue to the next iteration. If they're close enough, then it means that we have a good match. So even if we progress any further, probably we wouldn't come and see any difference. So at least on the meta model approximation, we cannot improve any further, and we should stop. Also, this allows you to come and say, yeah, in some parts maybe here I have converged, in some other parts I haven't converged, so I should try and put more focus on improving the Pareto front in this domain. We're gonna, now the only thing that we need to define, again, here you can see you have converged here, you haven't converged in some other location. So, okay, but what does close mean? We're gonna come and try and figure out how close are the two Pareto fronts. And be careful, we're not doing this in the design space, we're doing this in the objective space, okay? The design space, it's always a little bit, even though it's more natural to come and compare design solutions, because you don't know what the sensitivity around the design solution is never a good idea. It's always a much better idea to come, if you want to establish convergence, to come and compare with really what you care with what happens to the objective space. So in order to define this closeness, we're going to define the probability of superiority, which is what the probability of one design being superior into the other design by considering all the meta-model uncertainties. So now we're going to come and remind the fact that, yes, we get predictions from a meta-model. So in other words, we can come and calculate what is the probability using the meta-model that one design is better than the other. If this is close to 50%, it means that the two designs are indistinguishable. So the close, if this is far from 50%, it means that there is significant difference. So we're going to use this as our closeness metric of the performance for each objective. And how this probability is given is going to be given by, ultimately you can view this as a two-dimensional integral with respect to each objective when you get this objective by creating conditional realizations of your response. So we're going to come back now and remember that we don't have a single meta model, we have a family of meta models. So coming and creating conditional realizations, you can come and say how many of these realizations would this performance objective be better than the other one. So graphically how it illustrates, so this is sort of what your graph compressive meta model is, has some mean, some variance, has some correlation structure. So now you can come and create conditional, like you sample from this distribution, which is generally very simple to do. You just come and need to create some correlated, a Gaussian random number. So pretty much coming and getting this surface, it's very computationally inexpensive. So you can get conditional realizations of your response, and then pretty much, because you always are evaluating for specific x's, sort of you go and look for all the possible theta information that you have for those two specific x's, and then you come and evaluate what these objective functions are that correspond, or ultimately you don't care about what each of them is, you care about what the differences. what's the probability that this guy is going to be greater than the other guy. So using stochastic simulation, this is trivial to get, and sort of this is the information that corresponds to each of those planes when you cut with respect to specific values of the design variable. So you can come and you repeat this for many conditional realizations. Again, each of them just get new Gaussian numbers, and at the end you have this histogram, and very easily you can come and calculate what is the probability, considering all the uncertainties related to your meta model predictions, that one design is better than the other with respect to the specific objective. And as soon as you have this information, okay, then we can come and say, okay, what close means. We want one point of the current Pareto front to be close enough to at least one point of the previous Pareto front. In other words, we don't come and compare that guy and that guy, but we compare this guy and the one that's closest to it. This is why you calculate the minimum of the maximum of this probability, maximum over the two performance objective, minimum over all the points to go and pick the guy that's closer to you, and this is our convergence indicator. So for each of the points, you can come and calculate the convergence indicator that's going to come and tell you how close potentially you are to the previous Pareto front. If you want to globally come and evaluate convergence, you can come and say, look, I want this to be smaller than some threshold, and after, if this satisfies, it means I have convergence. So this takes care of characterizing what's closeness with respect to the two Pareto fronts and characterizing the convergence. Now, the other thing that we need to address is, okay, how you going from one iteration to the next one, how you're going to come and select your new experiment. So I'm going to come and use my sample-based design of experiments, what I already have talked about. So we're going to get some samples based on some preference density. We're going to keep some of these kind of samples based on some utility metric, and then I'm going to cluster them to the exact number of samples that I want. So let's say that I want to add 200 more experiments. I might start with 1 million here, bring it down to 500,000 here, then cluster them to the 200 that I really wanted to add into the next stage. But really, this is the trick where you have an augmented space that has two elements, design variables and model parameters, that have really different characteristics in terms of what are the new regions that you try to explore. So our preference density is going to be separately defined for the design variables and separately defined for our uncertain model parameters. So let's come and talk a little bit about what this preference density is going to look like. So during the second iteration, you have identified this, and also you want to visualize in the design variable space how these Pareto points are looking at. So evidently, domains that are closest to the current Pareto send, there might be a little bit of a bigger interest, because maybe something here wasn't identified to be anywhere close to the Pareto front, so maybe it's not of any importance. So you should still come to cover all the domain, come out of your 200 experiments, maybe add 20 or 30 non-explored regions, but you should focus more on your effort to better explore the regions of interest. So you have this, you can sort of, let's say, throw a kernel density, and then you can create this preference density to get more new experiments. But and a different complication. Okay, do we care about solutions that are close to the previous one? So in other words, do I care for parts of my Pareto front that already have converged? So, and you can again come and try to evaluate this on the design space. Okay, maybe this guy is close to that, so maybe I shouldn't include this guy in creating my kernels for setting any experiment. But it's much easier, much better idea, not much easier, it's much better idea to actually come and do it in the objective function space, because coming and defining closeness here is not, it's going to be a little bit arbitrary. Here we have already a measure that allows us to define closeness, which is that convergence indicator that is related to the probability of dominance. So in other words, I can come and exclude for the new design of experiments the points where I already think that I have converged. This I think my meta model does a good enough job here because I haven't been able to, even adding more experiments to identify new regions. So probably I shouldn't care. So rather than having this as preference function, we exclude these three guys, and we end up with this new as a preference function. As soon as you have the samples, yeah, you can throw like something like a kernel density, and now you have what your preference function looks like. So this is what you do for the design variables. For the model parameters is a little bit different because here you primarily care about calculating accurately your performance objective, which is probabilistic integral. And in that case, okay, well, regions that contribute more to the integral should be of higher relevance. Then your preference function really should be your integral. So this is actually, if you're familiar with an important sample, this is exactly your important sampling density. So, and because you have two objectives, now you can do a mixture of the important sampling densities that would correspond to each of your performance objectives. But now combining the two different densities, you have like your preference function, your preference density for coming and throwing new candidate experiments. And the thing that we haven't talked about yet is, okay, what should be our utility metric? And this is a little bit of a simpler. Remember, pretty much your Gaussian process, it tells you, actually what is your probability model because for Z, again, this is a probability model only because of the meta model uncertainty. We don't care about what happens with all the other uncertainties that are inherent to our problem. Here we're looking just with respect to the meta model uncertainty, like that sigma y that we had before. And we can come and sort of propagate that uncertainty to age. And we'll try to do something simple. So this is a first order, Taylor-Series approximation. And then this is pretty much the variability of my performance function that stems strictly because of the meta model uncertainty. And we can use that as a utility metric. When I say high variability, means that pretty much I have bigger influence of the prediction error that comes from the meta model. So these are utility metric. Now I'm complete. I can go and implement my iterative algorithm. We addressed the two important questions: what was my stopping criteria based on the convergence, and also how I'm going to do my DOE. And the DOE with the preference function, the utility metric, now we have all the tools for the sample-based DOE. Really quickly, let's go into an illustrative example, and here I'm going to try to mechanical engineering problem, a car driving on a rough road with we use a spectral characterization of pretty much all the characteristics of the car we consider to be uncertain, and we try to design the bilinear passive suppression system, suspension damper for the car. My two objectives: one is going to be the passenger comfort, the comfort of the driver, which we can measure if the acceleration or the RMS acceleration, since you're driving on a road that's characterized as a stochastic process, probably that the RMS acceleration will exceed some acceptable threshold that tells at what point will the driver start being nauseated. My second objective is going to be what we call the road halving, which is the average force that's created between the front and the rear tire force. And now this is my initial performance objective. Now we can come, as soon as we come and use the meta model, we can come and modify them, and you can see here, this is where, like you started again, we use a log normal fragility for the passenger comfort, and you can see that something comes and appears in the denominator. This comes directly, it's the infusion of the uncertainty that comes from the meta model. For the road holding, actually, you can prove that the uncertainty, the meta model, if you're just looking at expected values, is not going to come and appear. So one objective really modified, the other not modified, coming by incorporating the meta model prediction error. And if you wanted, you can easily come and calculate the derivatives. You're going to look, something like this, but you have all this information readily available for your meta model formulation. So quickly, some illustrative examples of how, and some illustrative results of how the iterative process works. This is the Pareto front in the first iteration. And here, going from the first to second iteration, so after we update the meta model, this is how this Pareto front ends. So this is still evaluated at the exactly designed configurations, but because you have a more accurate meta model, the Pareto front itself, you have better prediction accuracy, is going to move. But after that, you update also the optimization, so you end up with this black front. So in all reality, you come and compare, hey, did the repeating the optimization come and change what my expectation of the Pareto front is? And so you really come and say you move from the red Pareto front with the meta model at the beginning of the second iteration to the black Pareto front after you repeat the optimization. Evidently, you haven't converted yet. So you can repeat, and this is what happens in 5 iterations. And this is here we evaluate the performance with the meta model. But let's say that if you want to come and evaluate the performance using the actual model, even that has convergence characteristics. Of course, you don't know this. You don't have the luxury to evaluate this. Your convergence is really is evaluated using the performance using the meta model. And here we come here and we compare our meta model driven solution, which are the black circles, with a reference solution, which we got with extensive computational efforts of 365,000 model evaluations, as opposed to 3,500 model evaluations with our implementation. And you can see that you have a very accurate prediction of your actual Pareto front. And this is not just a trick. You can come and do multiple runs of this algorithm. And in all the cases, you can see that you converge very well in the Pareto front, in the actual Pareto front. And here is a comparison with what is another surrogate model-based optimizer, especially for expensive multi-objective problems like we have. And these are the green circles, and you can see that, some parts, and even though we used not just 3,500, like 10,000 model evaluations, some parts of the Pareto front you approximate very well, and some other parts that correspond to a rare event simulation, because our objective one has small failure probabilities, to see that you not do as a good job. So overall, very good news. With these iterative applications, we converge with a small number of evaluations of the actual numerical model, and we match pretty accurately the reference solutions, and we do much better in terms of both computational efficiency and accuracy of other competing state-of-the-art tools. Now let's move very briefly to a different U2 task, and we'll talk a little bit about stochastic sampling. The setting is the same. I'm going to remove my design variables out of the question because I'm not doing design anymore. So I have a system that has some uncertain model parameters. Ultimately, my goal here is to get samples from a target probability density that is related, of course, to your prior information and also to your system function. These appear, for example, when you try to do important sampling or event simulation to subset simulation, or even when you do Bayesian analysis. In this case, and for Bayesian inference, this would have been your posterior distribution, and this age of system functions would have been your likelihood function. So we try to get samples from this target density pi of theta that involves a function that is related to the response of my expensive to simulate model. So generally, there are different numerical tools that you can use, injection sampling, MCC. Generally, all the underlying similarity of all these tools is that you use trials, or samples from some proposal density Q of theta, to be able to simulate samples from your target density phi of theta. And the efficiency issue, you're as efficient as many trials as you need from Q of theta to get one independent sample from pi of theta. And generally, this is a non-trivial task. The better Q of theta, of course, resembles pi of theta, the more inefficient you're going to be. But doing that selection is really non-trivial. So what we're going to come here is going to come again, rely on a surrogate model. So we're going to come and replace our computationally expensive model with a surrogate model so that we can do trials very efficiently. Of course, this means that you come and change a little bit about what your target density are. And also you have to be cognizant of the fact that, how does my original target density is related to this approximated density that I have with my meta model. Now, another trick that these problems are very, frequently so challenging. In other words, when your prior to your posterior really change, that many times they need to be done in using intermediate densities as sequences. So rather than trying to do a big jump, you try to do smaller jumps using some intermediate densities. And because the difference between the intermediate jumps is not as big, you can come and use information from one to help to guide, select proposal densities to get information from the next intermediate density. Of course, your ultimate goal is to come and converge here. This appears a lot in cross-entropy importance sampling if you have transitive MCMC for Bayesian inference and so forth. More on this if you have questions, we can talk a little bit about later. But this is how the iterative application would look in this case. You get some experiments, you develop your meta model, you use now your meta model to get samples from your target density. My preference when you do this is to really come and rely. Most people would go and do something like MCMC. I really prefer to use a rejection sampling for this type of applications for two reasons. One is that it really gives you independent samples. If you use MCMC, you'll have to have in the back of your mind that there is some correlation that comes. And also the fact that you can come and exploit the vectorized characteristics of your JPM to do independent trials. In MCMC, sort of, unless you have multiple chains coming and parallelizing your MCMC is a little bit more challenging. For rejection sampling, because you really come and do independent trials, you can easily come and vectorize, parallelize anything that you want to do, and then you can, exploit the fact that you have a meta model that can allow you to very easily, do vectorized calculations and create simultaneous multiple predictions. So how does the iterative implementation work? So you do this once. After this, you come and evaluate, hey, have I converged? If you haven't converged, you proceed to the next iteration. You get adaptive design of experiments, and you repeat this process. If you have converged, then you can either come, you stop, and you can come and say, well, okay, then this is my target density, or you can come and do one more step, and now using this density, which you think it's a good approximation of your actual density, you come and use as a proposal density to really come now and get samples from your actual target density. This sort of comes and circumvents any errors that might come from your meta model if you really care about getting a sample from your actual density. Now, the stopping criteria, straightforward. You have converged to two different densities, the two iterations. So you can figure out, okay, what's the discrepancies between the two densities. You can use something like the Hellinger, a distance to go and measure this discrepancy. And with respect to the DOE, again, we're going to come and use the sample-based DOE. Our preference function, evidently, is going to be our target density. This is what our UQ task thinks that it is important. And in terms of the utility metric, we're going to separate it into two. This is what we call, target-based DOE, where you really try to improve the accuracy around your target. And we're going to pretty much use exactly the same utility metric that we had before, which is going to be the propagation of the uncertainty from your response into your system function. And now we have another, a supplemental DOE that the reason why we have this DOE is that this DOE really comes and looks at the final density that we use a target density. But we say that we're going to have some intermediate densities that are going to help us get to that target density. So really, we need to have a DOE that's going to take care of the fact that we don't want to get lost stepping in the intermediate densities before we reach the final target one. So in this case, your preference function is going to be the intermediate densities, and really our utility metric is going to be the differential entropy between your prior and posterior predictive characteristic of your emulator. Pretty much having a low value for this is you have a domain where you haven't yet extracted enough information from your experiments to change your predictions. And since you already haven't since you haven't selected enough information, maybe it might be a good idea to come and not consider. So combining this, two different DOE approaches, you end up with a final DOE. So you get some samples from one, some samples from the other. That gives you your new experiment. So, and very quick some applications. We're going to look at this, in terms of rare events, estimation. So ultimately, your target density is your integrand that involves the system of functions, the indicator function. So after you converge, then how you can evaluate this rare event, one is to come and completely rely on your meta model, which means that you're going to get all the errors that might exist in the meta model. You're going to propagate them. The other thing is to just rely on the meta model to formulate your important sampling density. Then you're going to come and use your exact system to evaluate what your response is. So your meta model simply gives you a better important sampling density, it reduces the computational burden of your stochastic simulation. Here, your stochastic simulation uses the meta model itself. Here, we're going to come and use the actual model for the stochastic simulation. So, couple of examples. One is going to be this truss. The other is this floor isolation system. On the truss, we have two variants, depending on how if we look at the response only at one point, or we're looking at sort of a system reliability in the maximum response across different points. And this is how the application works in different iterations. So DT is my threshold criteria for convergence. You can see as the iterations of the algorithm changes, the entropy of the difference of the densities that I approximate really comes and converges and reaches a plateau. So even if I continue and added more experiments here, I really don't expect to see any significant difference. So one way to evaluate convergence is to come and have some absolute threshold the way we did, or after we saw it, we realized, yeah, maybe we can just come and see like the relative improvement across the iterations. So this is how, this is the entropy between the approximated densities. This is how the approximated density compared to the actual PDF. And you can see here like similar characteristics that we had before, that you have some rate of convergence that quickly reaches the plateau. And this is a comparison across iteration. What would be the estimate of the failure probability? You see what we're calculating things around that 10 to the minus 4, 10 to the minus 5. So relatively rare events, and you can see that you quickly converge. Either you come and use your meta model in this. Here you just rely on important sampling coming from the implementation. You use the exact system model. You can come and see, and you really come and the two come and merge one another. Here comparison, how do we compare in terms of other things that other people have implemented, and again the really important comparison with Monte Carlo simulation, you can see that with a significantly smaller numerical burden, you come and get something that is, even though we talk about some 10 to the minus 4, really a good accuracy of the competing approaches. The only approach that polynomial chaos Kriging approach that beats us, you can come and see, does come and give a biased prediction. Of course, I wouldn't say that this is that important. The difference between 3.2 10 to the minus 5 and 3.5 10 to the minus 5, in terms of making decisions, is not that significant. But from the mathematical perspective, yeah, we do get, we've shown that we get unbiased results. Let's wrap it up. So conclusions: the surrogate modeling can facilitate significant computational benefits for UQ applications, and Gaussian process meta models are especially relevant in this context due to the holistic treatment of uncertainty. And this is the important, outcome from this study, is that we really should try to adaptively control the meta model accuracy, especially coupling with an adaptive DOE, with the ultimately goal to converge to accurate solutions, leveraging perhaps inaccurate meta models in the process. Of course, at the end, they have to be accurate enough in your domains of interest, but you can adaptively control them. For design understanding problems, especially looking at the augmented input space is especially relevant. And in general, the sample-based DO, even though it will not give you the optimal new experiment, it gives you a suboptimal one that works pretty damn good, especially if you consider that you can very efficiently do this theory. And with that, thank you very much for your attention. And I should point out that in acknowledgement, you're only good as your students are, and this is primarily work of Ziz and Zhang with some of the preliminary work coming from Juan Camilo Medina.